All right, thank you very much for the invitation. So yeah, as said, I put also the subtitle there, with from the precision era towards the accuracy era of cosmology with DESI, because that's what I've been working on during my PhD in Barcelona. And so I know that in this audience, I don't need to tell you the difference between accuracy and precision. But you know, as we all know, precision means you have high precision means low statistical error. High accuracy means we have small systematic error. And in the end, we want to be accurate and precise, right? We all heard this term precision era of cosmology, right? And it mostly emerged with the Planck measurements, where we get the CMB temperature to very high precision, and even the fluctuations of order 10 to the minus 5, and we can measure the multiple the power spectrum. But if you look at if you do a search on NASA ADS, how often this term arises. Actually, the first one I found was by Wayne Hu, and it's related to the CMB, of course. But if you compare it to the term accuracy cosmology or accurate cosmology, there's only a few works using that in their papers, one by Peebles and Licia Verde. And I asked myself, I wondered, like, why is there such an overabundance of precision versus accuracy? And I think think about it, because claiming precision means we have a small statistical error and we have tight constraints on model parameters. And that's relatively easy, because that comes natural out of the analysis. Whereas claiming accuracy is more involved, right? Then you have to prove that you have a small systematic error, and your model is a good description of reality, which is hard. And even in science, we will never reach that statement that we say this is exactly true. So you cannot really make a scientific claim that you are accurate, because it's always depending on better data, better modeling. So in that regard, I would like to discuss the recent DESI results, the BAO results in particular. I do a quick introduction to cosmology from alpha to omega. So that will take only 95% of my talk. Yeah, just kidding. Then an intermezzo on DESI BAO cosmology results. I will briefly mention them. Then I go present the DESI end-to-end pipeline. Don't worry, not the whole end-to-end pipeline, but I will go through some of the details. So that will make the other 95% of my talk. And then just show how we tested these systematics in the DESI BAO analysis before I conclude. All right. So just to start with, we're living for a while with this lambda CDM paradigm, which I would say, there are many ways to phrase it, right? But I would say it resides on three very fundamental pillars, which are the cosmological principle, you could argue, that gives us the metric. Then general relativity, which relates how stuff behaves within that metric. So that gives us the Friedmann equation. And finally, the standard model of particle physics, which tells us what are the components of that stuff that are in the universe. And then we can neglect all the things that decay in time and only use the stable particles, and say that all the protons and neutrons are just baryons. And then we have the standard. Then we go ahead with that. Then there are some assumptions that are not as solid, I would argue, which are maybe inflation, the cosmological constant or dark energy problem, and cold dark matter, which we don't really have good intuition or really fundamental understanding or microscopic understanding of those. Then we put this all in the basis of parameters that we call omega, vector omega, which includes parameters describing all these ingredients. So now, how do we make observations? So here's the history of the universe with the Big Bang and recombination and large-scale structure emerging up to z = 0 or today. And there are some things that we can directly measure from there. Okay, so the CMB measures the photon temperature and photon density. And we can relate it to infer the neutron density from that. Then with the anisotropies, we can fit the model to these spectra and can infer, given the model, all the other parameters. Then we have BBN measurements that measures the omega baryon, measures some abundances, and we can infer omega baryon. We have supernovae that give like a direct measure of H0 if you trust the calibrators, and gives a hint on the evolution and omega lambda. If you look at the BAO analysis or full shape plus BAO analysis from eBOSS and DESI, you can get H0 RD almost directly, and infer other parameters from that. But what are the assumptions behind? So you have kind of raw data, right? So for Kobe, you have the frequency as a function, the intensity as a function of frequency. You can fit in a black body, and you get the temperature. So for anisotropies, you also get the CMB power spectra. That's already not the raw data, but that's already the reduced data, the CL. And then you can infer the angular position of the peak, and maybe other parameter things that you can get directly infer from that. Then you have some spectra. You can measure spectra, again, intensity as a function of wavelength from very pristine gas clouds, and infer the abundances of deuterium and helium. And then for S supernova, you also measure some brightness as a function of time, and you can measure the magnitudes and the evolution of the luminosity distance, and with that you can kind of measure h of z of the normalized h of z. Then you can measure spectra for spectroscopic surveys, fit redshifts, and then get some reduced data, the summary statistics, and measure the BAO and have another geometrical quantity from that. So what's the point of that? Oh, sorry. Basically, there's a hierarchy, right? I have raw data, then I have reduced data, and then there are some things that I call alpha here that are measured sort of directly from that reduced data. And when I assume a model, I can infer the model parameters, which are the omega. Okay? So that's sort of a separation between this alpha and omega. Let's jump to the cosmology results. So last year we published the first BAO results, and this year in March we updated them with the year 3 BAO data. And I want to show this figure, which is the first figure in the cosmology paper. And I really like it because it shows what kind of precision measurement this BAO actually is. So on the x-axis, age of the universe, this relates to the co-moving distance, which here, this is assuming a fixed value of the sound horizon. What we actually measure is dm over rd, but this is just displaying it for rd of 147 point something. These are the 2 sigma errors of these dm that we measure, okay? And when we do the BAO, we identify this feature in the clustering data, and there's a perpendicular component and a parallel component with respect to us, the observer. And the perpendicular component basically gives us this measurement. This is the 2 sigma error bar, and the parallel component, the parallel component gives us an idea of the expansion rate itself, which is basically the derivative. It's the slope of that curve. It's the scale factor as a function of the age of the universe. So the slope of that curve that is measured here, that's what we measure. And this is the 2 sigma error bar we have on the slope of that curve just from the parallel BAO. So by eye, you cannot really identify it. Here you see the difference between dark energy plus matter, so the accelerated expansion, and matter only. So there's a clear evidence for accelerated expansion. And this evidence that we found, which for evolving dark energy, you cannot distinguish it by eye here. It's beyond what you would need to zoom in. So let's zoom in. You see here the BAO peak position that is measured from the different redshift bins, from the different samples. And you see a beautiful, clearly resolved BAO feature in the correlation function at each redshift bin. And these are the relative positions. So this is what we call the alphas, or the volume average distance over the RD with respect to fiducial cosmology. Okay? And this is showing the Planck lambda CM as the solid line at 1, and the deviation from that is what is preferred by combining DESI with CMB and DESI DR5 supernova. And then you get this this slope for in dV. You get that it's lower than the lambda CM prediction, and you also see this signal on the parallel distance, or the Alcock-Paczynski, the anisotropy. You also see the improvement from DR1 towards DR2, which are the solid versus the transparent points here. All right. And yeah, what was found that if we combine DESI with CMB in the W0WA plane, this is where the contours lie. And when combining with different supernova sets, you get different degrees of discrepancy with lambda DM. Right, so what this was created by Claire Lamman, like something has to give. There's still clearly some pressure on lambda here. But yeah, how robust is this? Let's dig into, that's why we're here for, let's dig into all the assumptions that went in and see where there's room for change, or how robust are these assumptions going in. All right, so let's come to my next part. What do we actually measure with DESI? So DESI is a powerful spectroscopic instrument because it has these 5,000 individually controlled robots that can at the same time, with one exposure of 20 minutes, we get 5,000 spectra. And that's how we get 50 millions of spectra over the 5 years of DESI observing. Here, nicely presented by the Kyoto BAO Ban. If you want to know more about it, you can check out this blog post. And this is a zoom into the focal plane, so we can really move the robots and target the fibers exactly to where are the targets that we want to observe. All right, so we need to have targets for that. So we need imaging surveys that tell us where are the galaxies that we should point the spectrograph to. And there are 2 billion of them. And we cannot target all of them, so we need to do some target selection. So based on the photometric data, we need to apply some cuts to select the most interesting galaxies for us, which here in the case of luminous red galaxies, it's showing the stellar rejection cut to basically distinguish the extragalactic objects from stars, from Milky Way stars. And there are many other cuts. To reduce this 2 billion to just 50 million galaxies. Then we point the telescope exposure per exposure to get the spectra. This is one reference spectrum, sorry. And we can, from repeat observations, we could actually identify what is the error on the redshift estimation. And what is found is that generally for the BGS and ELG sample, there's 10 kilometers per second statistical error, and for LRG and quasars, it's up to 50 kilometers per second. There's also some catastrophic redshift failures due to line misidentification, but this is really a minimum number of galaxies in the ELG sample, and that can be modeled also with repeat observation, and there are different weights to account for that, and see how it impacts the result. And yeah, so these are the redshift uncertainties. Then there's the density fluctuations in the targets themselves. So here you can see that the footprint for DR2 that was actually observed has some denser regions, or regions where we have more observations, whereas other regions have not been scanned as often as the other regions. So how can we account for that? So first of all, there is imaging systematics that are inherently there in the imaging catalogs. And this has several reasons. There are, for example, we are using different sources of imaging catalogs. So this is the northern part here, comes from the BAS plus MZLS instrument, whereas the south here is from DCAM, and some part within that its footprint all actually comes from DES, which is has higher, it resolves even fainter objects, and we need to kind of correct for the fluctuations that are within the different target samples themselves, and also for each target sample see whether there are any trends in the data of the number density of galaxies that are correlated with some values that we know this correlation shouldn't exist. For example, the galactic extinction should not have an influence on the number of objects, the clustering of objects, as well as the stellar density and the depth in the G band. So there are the raw measurements. So these trends are visible, and we can basically construct all these maps that depend on imaging properties and use either linear regression or random forest or other regression tools to correct for some of these quantities. And so here it shows the correction where it works the least good for these, from many other quantities that I will not go into detail here. Then this footprint is not uniform, right? So when we compute our clustering, we need to create like a different catalog, like a zero catalog that has no clustering but has the same underlying footprint and number density, average number density. Okay, and we create these random catalogs, that's how we call it, just placing random objects that have a much higher sampling than the data itself. So you reduce the Poisson noise, and that gives us the window function through which we see the universe, and we need take this into account when we convolve the models with that window function. Then that's not the only incompleteness systematics. Then there's also the fiber collision. So there are pairs of galaxies that are so close together that we cannot observe them in one pass. So when we create the list of targets that are observed, we can have different realizations of that observation strategy and put that on mock catalogs. These are called ALT-MTL, Alternative Merge Target List, and then we can basically reconstruct what is if we have a mock with complete number of galaxies and we apply the targeting scheme in different ways, what is the fluctuation that we get? And as you see, it's very hard to really model that. So for the DESI full shape analysis that came out in November, there was a conservative cut was put on this theta, on the angle of that basically corresponds to the minimum separation you can have between two adjacent fibers, and that also changes the clustering statistics. And you can take it into account into the modeling. So then, when we have the field, the 3D galaxy field, we get this clustering statistics. It's like we count the number of pairs that have the same distance and have a certain orientation, and then we can just create a histogram that lists how often does a certain separation and angle occur in the catalog, compared to the random catalog that I talked about earlier. And then the Legendre transform of that just gives us the correlation function multiples. So this is what this looks like for BGS LRG1 and LRG2 in the DR2 data. And we see above the monopole and then the quadrupole. But this already has reconstruction applied for it. So what we do, we apply, to the catalog that we have, we apply the so-called reconstruction scheme. And the thing is that the BAO signal, which is a pristine signal that is imprinted in the early universe, due to nonlinear motions, it sort of becomes biased, or it distorts itself. And to get rid of that systematic of nonlinear motion, we basically estimate the velocity field given the density field, assuming a linear bias value and a growth rate evolution, and then we can just move the galaxies to where they should be according to the in the initial field. And this was tested in several papers, and what I would like to highlight here is that for the BGS sample in MOX, for example, we could show that by applying this reconstruction, for the BGS, there's a systematic effect of 2% from the nonlinearities. And by applying this reconstruction, this bias could be mitigated. And you actually see it in the power spectrum, that the reconstructed power spectrum, the wiggles are slightly off from the pre-recon one. And if you do the comparison with MOX and different HOD models, so this is the paper by Juan, who also is here in the audience, then for post-recon, we recover the correct BAO position, whereas for pre-recon we have this bias due to nonlinearities. So I would argue that reconstruction is one of the most important tools to remove that systematic uncertainty. Also, there was already a discussion on blinding. We use the blinding scheme that's at the catalog level, so we shift galaxies along the line of sight, and there's both a geometrical shift due to the expansion history and a density-dependent shift that makes this use of the same reconstruction methodology to imprint a different growth rate and in a model-independent way, and this is something that I worked on, that we proposed when I did my PhD, and that's the collaboration meeting in July 2019. And we published this paper, Blind Observers of the Sky. And there are even more works right now. So this was also validated on DESI MOX later on by Windert, and Edmond proposed a catalog level scheme for primary non-Gaussianity, and also for power spectrum plus bispectrum. This blinding was shown to work well. What is the impact of these systematic uncertainties on the BAO analysis? This is showing the deviations of these BAO measurements, the isotropic one, for different sets for differences in the pipeline. And what I really want to put the attention to is unweighted. So if we neglect all the weights, so the systematic correction that I showed for redshift failures, for imaging systematics, if we just remove all of that, then we get the unweighted, and you see the BAO position barely moves. It's really, really robust to that. And also, when investigating different data sets, so different subdata, the scatter here is all within the statistical estimation, so there's nothing weird going on. And also the modeling assumption here, they are very, very robust, both also for the anisotropic part. And even the fiducial cosmology assumption was tested, so there are different sets of MOX, of the Abacus MOX, that were investigated here. And these are the shifts on the parameters for all the redshift bins. And I would like to stress this part, which is the best fit WZWA, which was, so the whole analysis, including reconstruction, was redone with the best fit from WZWA, and it barely changes the results in the BAO. So yeah, this DESI DR2 BAO is just the start. There's still DR1 analysis going on. For example, to determine the systematic error from the fiducial cosmology assumption in for the results that were released in November. So this is both for the shape fit analysis, which is like the BAO analysis, but extending it towards the full shape of the power spectrum, and which also gives like a compressed data set that can be used for cosmological interpretation, and also for the full modeling approach, where we directly fit models to the power spectra. So this investigation is still coming, and also cosmology from higher order statistic, including the bispectrum, and also the full shape analysis for the DESI DR2 is coming soon, and I'm involved in that within the group in Edinburgh. And so one quick result I wanted to show is that for that, when I did a preliminary Fisher forecasts for when we use the full shape on that DR2 paper. So the full shape alone would give, for the power spectrum, would be as good as the BAO alone. And when including the bispectrum, it could increase the significance of this W0WA up to 3.2 sigma. When combining with the BAO, even further. So yeah, there's really interesting things coming soon. And yeah, I will close here with my conclusion. So I presented different systematics and their mitigation schemes. So server-related are these spectroscopic systematic, or the uncertainty on the redshift measurement themselves, and line misidentification. Although I didn't go into the details, I have to admit, because it's hard to cover it all. But, then there's the photometric systematics or imaging systematics, incompleteness systematics, and what I think is astonishing, or the really nice result, is that none of these impacts the BAO. Even if we don't correct for anything, the BAO remains stable. Which, yeah. Then for modeling, there's also, of course, there's confirmation bias, which can be mitigated by blinding. We had this discussion. I agree that it's not 100% sure that you will mitigate it by blinding. Of course, you need to know what you're doing. But I don't know any better way of mitigating this kind of confirmation bias, because no matter what we do, we have it all, right? Then there's this nonlinear evolution, which we mitigate with this reconstruction. There are other theoretical modeling choices. I didn't go into detail, but there's plenty of literature on that, and the BAO shows to be very robust in that regard. There's the fiducial cosmology assumption, which is negligible, and we can redo it when we have a best fit that's away from LCM. Just redo it with that new, and you see that there's barely a change. So in that sense, I would argue that the BAO analysis is very robust. And one thing I would like to mention is that I believe it's a good idea to, before assuming any model, look at this alpha, like what is the parameters that are really constrained by the data themselves. And if there's a tension there, then we know there's something going on. There's something really wrong, and no model could accommodate for that. Whereas when there's a tension within the model, but the data sets are still, there's no obvious discrepancy between them, then it's harder to say whether it's really the wrong model or is systematic. So that's why I like this approach of looking at the compressed variables where tensions that are really model independent are more visible. All right, and I will close it here.
Thank you for very interesting talks. Some other questions?
Thank you for a great talk. So if you go back to the slides where you have the W0, WA ellipses with both the supernovae and the BAO. So there's one, maybe potentially trivial, but maybe less so discussion we could have here, which is if you look at the axis of these ellipses and you see that the deviations from lambda are exactly along the major axis of these ellipses, which is obviously just another way to put it is along the direction of where your uncertainties are the biggest. And right, I mean, it only takes underestimating maybe one of your long list of error bars, and you would by definition move along that axis, right? And for supernovae, we found very simple ways you can get in that trap, which is if you happen the relative calibration between a low and high redshift data set, they immediately will move in that direction. I'm not saying that that's what's happening, but it's a very it's alarming that that's the way the data go. So my question to you is there similar? Is there any effect that keeps you awake at night, thinking that this could be on the BAO side that could move you in the same direction?
Yeah, that's a very good question. And it's true that I cannot really talk for the supernovae, but sorry, one slide. Yes, so let me maybe first show that slide, because we also looked in that paper on the impact of not including any supernova, right? So this is showing that DESI plus CMB plus DESI DR5, so that's the that's the supernova, the green. But then if you replace the supernova by 3 times cross 2 points, then you are still in this quadrant of the constraints, where if you yes, so that's the yellow part, right? And here you see you will still recover lambda CM within 2 sigma. So yeah, I agree that it's true that lambda CM is exactly within here. From all the tests that I showed on the BAO, I think that there's none which actually looked at it. I looked at all these systematic plots, and I looked like, is there any row that would actually bring me again towards lambda CM? And I didn't find any. This like all incoherent shifts, like that don't go all in the direction that I would say, oh yeah, this would recover lambda CM even better, right? So I think from the BAO side, we are in that quadrant. DESI plus CMB indicates we are here, but I would also not bet everything on, oh, lambda CM is rejected. I think, from DESI alone, lambda CM DESI alone doesn't throw away lambda CM in any way, right? It's just this combination of data. And what I really like is to look at the data itself and see the models compared to that, right? So the top shows the BAO measurements, and the lower shows the supernova. And here you see that it's true that the supernova at the low redshift, for example, Union 3, DESI DR5, they have some high point here in mu, which seems to drag towards going away from lambda CM. This is not present in Pantheon. But all these supernova in the modulus, they show something consistent of a lower prediction in this redshift range here. And I think there is them.
But that was my point.
Yeah.
The supernova, it depends how you combine with the hierarchy. So if you have a 2% offset in your calibration, you get exactly that. So it's, I don't say I wouldn't put too much faith on this data set. That's why we mentioned in the previous session that there are larger data sets, much more carefully. One survey alone that would maybe solve this. So again, I guess my suggestion is not de-emphasize a little bit the supernova in this conclusion. I think there are problems.
Yeah, that's true. That's why we were just checking all of them and see what are the difference. But it's true that these differences should be sorted out. Yeah.
How do you know that your data are accuracy and not just precise if we are living in a cosmological parameters tension? Because in a perfect world, where you have very accuracy and precise data, tensions don't exist. So how do you know that your data are accuracy?
Yeah, I mean, I would not know it for sure. That's the point. That's the thing about accurate. You cannot know for sure whether you are accurate, right? It's like an unscientific statement. If you say my data is accurate, you say I know the answer, but we don't know the answer. And that's why we can say my data is precise. I can demonstrate it's precise. But of course, we want to do everything we can to get it as accurate as possible, and we can only do our best in doing so, right? And then, of course, when there are these tangents, that's why I said, let's look at tangents that arise from data itself without assuming a model. And that brings us, then we don't need to ask ourselves anymore, is this tangent coming from we have the wrong model, or is there some systematic? If we look at this, what is actually constrained by the data? For example, in this plot, this mu thing, you can actually convert it into a luminosity distance. And the luminosity distance is directly related to the angular diameter distance. At least in a flat universe, they just divide by 1 plus z, and you can see, and you can check whether the data points that are in the same redshift range between the BAO and the supernova, they agree. I don't have that plot here with this conversion, but all the supernova samples in the redshift bin that's overlaps between BAO and supernova, they agree. So I think that's the strength that we know. In that redshift range, we have agreement on that quantity.
Yeah, because I remember that when I saw for the beginning the BAO's results, I remember that you don't publish just constrained cosmological parameters using BAOs. You just publish the data with BAO, CMB, and supernova. And right now with DESI, for example, it's for me it's great that you are constraining the cosmological parameter space using just DESI. This is something that didn't happen in the past. I don't know, maybe a couple of years ago. And this is something great that you can use in DESI very much.
Yeah, I agree.
So I have this question. Seeing this plot, so when I'm seeing about the green dashed plot in the first one and the magenta where DESI plus CMB is there, it seems when you remove, when you add lensing, then dynamical dark energy is there. So it's not DESI, but CMB lensing that is playing a role. Does this plot say that? Do you agree?
Yes, so here you're comparing the green dashed, which is here, with the violet or purple. Yeah, I mean, it's a mild discrepancy. I think the tension, if I remember correctly, with lensing, this tension is of order 3.1. Without, it's of order 2.5 or so, right? So it's still there. It's the lensing just adds a little bit to it.
So
And
the tension is not there in DESI with dynamical dark energy, with lambda CDM, right? If you see the green curve, then in DESI there is no tension with lambda CDM, but it is CMB lensing which is causing the tension here.
But not only lensing, also the DESI primaries, right? So if you look at the green dashed is here, right?
Ah, okay.
So this dashed black, that's DESI alone. I agree, there's no tension here. But as soon as you include the CMB, whether it's be just a compressed likelihood, just theta star and other parameters, or it's the full likelihood, including or not lensing, then you see this sort of tension. I don't know whether I would call it tension, but at least it's an intriguing difference from that sort of expectation.
Okay.
Yeah.
Thank you.
Hi, thanks for the nice talk. I have a question about the reconstruction procedure, because you say that you assume a linear galaxy bias there, and I mean I'm not working on spectroscopic galaxy clustering, but on photometric side I always hear that linear galaxy bias might be not enough for stage 4 service. So are you fully happy with the linear galaxy bias for this kind of reconstruction? And again, about the reconstruction, do you assume any model, cosmological model within the reconstruction procedure, or is it model independent?
Yes, so there are several assumptions going in, right? Well, you need to have first you need a model to put the galaxies in a box. So it's like a fiducial model that tells me how to convert angles and redshifts to a physical distance. Then there is the assumption of linear bias, which and the assumption of the growth rate, so linear growth rate. So the goal is only to remove the large scale, the bulk flows, which are very linear, when we use a smoothing scale of 15 megaparsec by default, to remove the very nonlinear stuff. And the thing is that the velocity, the nonlinear velocity, are coupled to the linear density, and you can remove that part. We don't remove all the linear velocities, but just that part that comes from the linear displacement field, or the linear density fluctuation that give rise to this nonlinear velocity. Of course, maybe there are better ways to do it, but we have, if you look at these papers, there you can play around with the bias values. The full shape of the power spectrum, they will be quite different between different reconstruction assumptions, okay? If you look at the full shape, yes, the assumptions matter. But there are even theoretical works by Martin White and Blake Sherwin, I think, where they say, okay, let's assume we have 10% error, 5% error on growth rate and bias, and even the fiducial, the background cosmology, and the impact on the oscillation on that feature is completely negligible. That's why we only use it for this BAO part and not for the full shape, because then it's true that we would not be able to be insensitive to these assumptions.
I'll just add one more thing to this, which is that so if you do compute the additional terms which go in front of linear bias with perturbation theory and stuff, you can basically show that they only become relevant at really large scales, which don't matter here. I think like they're like really large scales, which are just not interesting unless you're doing very specific kinds of things, so they don't matter as much.
Yeah, just one last question. So one of the plots you showed at the end, that was kind of showing the full shape analysis. You had an option where you added BAO to the full shape, and I was a bit confused by that, because don't you have BAO in the full shape already?
Yes. So, if I have BAO in the full shape, but here I'm adding the post-reconstruction BAO, which I don't have in the full shape. So imagine I would measure the BAO from pre-reconstruction and then combine it with the full shape. I would not gain anything, because that's already in the full shape. But since we use the reconstruction for the BAO, we can get tighter constraints on BAO, and that gives us like an advantage when we include that in the full shape. I must say this is Fisher forecast, and I didn't include the cross correlation here. There's in the BAO paper, in the full shape BAO plus BAO paper in November, all the full shape measurements were combined with the post-reconstruction BAO, and their covariance was taken into account, because of course there's a correlation between the post-reconstruction BAO and the pre-reconstruction BAO. But this covariance can be measured from mock simulations, and it can even be derived analytically. That's something I'm trying to do right now to get these forecasts correct. So, but yeah.
Maybe I'll come and talk to you why this is the case.